Welcome. This video I'll discuss the sheath heat transmission, and this is an important boundary condition for modelling of the plasma edge because it determines how much heat, how much power is lost from the plasma, and also how much power is then deposited on the surface. And so if the power is limited, then this will change the temperature. Alternatively, if the temperature is limited, then this will change the power, but it provides a very strong lever to change the solution at the edge of the plasma. Because the temperature then has an effect on all the other quantities, including the sheath itself. Because if the temperature changes, the sound speed changes, and so the heat flux and the particle flux also change. So it's a quite complicated nonlinear system, but the sheath heat transmission is quite an important factor. And so this lecture I'll discuss the ion and electron heat losses, and how energy is transferred from the electrons to the ions. So what we'll see is that in the plasma, the electrons lose the most energy. So the electron heat loss is higher than the ion heat loss. But inside the sheath, which is a very narrow layer, but there is a transfer of energy from the electrons to the ions. And so the ions arrive at the surface with more energy than the electrons. And so this is what's used in things like ion bombardment or modification of surfaces for industrial applications of plasmas. But it also has implications for sputtering of surfaces, because ions are accelerated and can hit the surface with very high energies. So there's a few good references for this. As with most things related to the boundary of tokamak plasmas or other fusion devices, there's Tankerby's textbook, and there's more recent work on kinetic modelling of the sheath. For example, David Zakaya. There's also Alex Chankin, just got us work in this area. Two kind of names to look for, and so this is just one example of papers in this area, because if you do kinetic modelling of the sheath, this can have quite different results depending on the scenarios. So here I'll mainly discuss the fluid modelling, so simple models of the sheath, but just keep in mind that kinetic effects can become important. So discuss in what we're talking about in the sheath. So we have a wall here, and in the sheath we have electrons and we have ions arriving at the wall. The electrons, of course, arrive first. So we have high energy electrons hitting the wall first, because they're moving so much faster than the ions. So the ions are coming in like this. So this ion is positive, and this sets up an electric field. So there's a region close to the wall of a width which is of the order of a few Debye lengths. So this is very narrow, so it can be micrometers or nanometers in high density fusion plasmas. And this is a very narrow layer compared to Lime orbits or the size of the wall. And in this region there are more ions than there are electrons, so it's not quasi-neutral. And there's an electric field, which I'll put in here. So here there's a strong electric field which is directed towards the wall, and this of course accelerates the ions. So the ions arrive here going sound speed. So V perpendicular to the wall is the sound speed or larger. This is the Bohm criterion, and they are then accelerated, and this provides extra energy to the ions. That energy of course comes from the electrons, and the electrons, what happens is they are essentially reflected by this electric field. So they experience a force which is away from the wall, or equivalently a potential barrier to get past. So high energy electrons can get through the barrier and hit the wall. Low energy electrons are essentially reflected back. And so you have low energy electrons are reflected, high energy electrons get through and hit the wall. And so it's essentially a high pass process for electrons. So what written here, so only high energy electrons can overcome the sheath potential, which I'm going to label VF, is this potential here. So voltage VF, or the potential difference between the sheath entrance and the wall, which is this electric field here. What this means is for these different species, so I'll consider the electrons first and then look at the ions after. So in many cases the electrons are relatively collisional, so they can be considered a Maxwellian distribution. We use approximations like the Boltzmann response for the electrons. So essentially have a distribution function, let's say of energy, or this might be parallel, say parallel kinetic energy. And what we have is a distribution function like this. And this would be like some distribution function of energy, and there's essentially a cutoff here where this is the potential of the wall, and so these electrons here are lost to the wall, and these electrons here are reflected, and so if we draw the velocity distribution function now, so this is like v perpendicular to the wall, and this is like the velocity distribution, so it's essentially a Maxwellian, because the collision time for the electrons is pretty small, and so in most cases you can consider them collisional, although not all, and there is a cutoff here, which is of course just the corresponding to the same energy here. So we have that the perpendicular velocity is like square root of 2, and now we have E times the energy divided by ME. So this gives the velocity. And again, these ones are lost, and everything else is reflected. So the distribution function looks like a Maxwellian with the tail chopped off, because all the high energy electrons are lost to the wall. So if you work out the power which this contains, so essentially it's by integrating up this component of the distribution function, you work out for a Maxwellian what the electron heat flux is. And it's called the heat flux, so it's in sort of watts per square meter. At the sheath entrance is SE, here is the sheath entrance. Hence the SE, and it's going to be different from what's at the wall because there is a energy transfer from electrons to ions, and this is given by essentially a combination of this from the drifting Maxwellian. This is the thermal energy of the electrons, plus because we're selecting part of it, we're selecting the high energy part of the distribution function. So it's essentially the integral over just the high energy part, and this gives a very small flux because it's just a small part of the distribution function. The majority of the electrons are reflected, and so in terms of the flux gamma, this is like particles per meter squared per second arriving at the wall. So there are lots of electrons arriving at the sheath entrance, but most of them are reflected, and so the ones arriving at the wall is this gamma, because this is also the number of ions arriving at the wall. Okay, so this approximation here. So the floating potential, so the sheath voltage, this is roughly 3 times the electron temperature. It depends on the ion species as well, so the ratio of the masses. For deuterium it's about 2.8, so for now we'll call this about 3. So this is also proportional to the electron temperature, as is this one, and so often this is written as a constant gamma, which is called gamma E, for the electrons, times the electron energy times the heat times the particle flux gamma, where this gamma E, this is the sheath heat transmission coefficient, and so the total heat which is lost from the electrons is given by essentially this combination here. So we have 2 ET from the shifted Maxwellian, this because we're selecting the high energy tail. There's also an extra factor of half TE from the pre-sheath, which also selects just some high energy electrons. And so gamma E is roughly this 2 here, plus roughly 3 from the sheath potential, plus a half from the pre-sheath. Which, because it's removing some of the low energy electrons, means that more power is lost for a given number of particles, because the particles that are being lost are the high energy ones, and so the total sheath heat transmission for the electrons is roughly 5.5. So now we'll look at the ions, and this is a bit more complicated because the ions typically are not very collisional, and so this depends on the distribution function, which is in general can't be assumed to be a Maxwellian like this, like the electrons can, and so this is quite sensitive to kinetic effects or to sort of non-local effects. So if you have ions which are coming from hot regions upstream, this can lead to additional heat fluxes. So in general this is much more difficult to calculate. But if we make the assumption that this is a Maxwellian or a drifting Maxwellian, so it's a Maxwellian which is essentially shifted. So if we then plot the perpendicular velocity for the ions as a distribution function, we're assuming that it's some kind of a Maxwellian, but it's shifted as this is the fluid velocity, of course. So U perp is like the average velocity towards the wall. So this is a drifting Maxwellian. So in this case, we can make the approximation that the ion heat flux to at the sheath entrance is roughly given by, so it's a combination of essentially the thermal energy, the work being done, to the kinetic energy, so half m u squared. So this is the kinetic energy and essentially thermal energy in terms of the heat flux through the sheath. At the sheath entrance, this of course is the sound speed, so ui is sound speed, as this gets another factor of ti here, and so in total, so this we again write as a gamma I times E times this, so we have another sheath heat transmission coefficient, and gamma I here is basically 5 halves plus another 1, so this gives 7 halves from this calculation. If you do kinetic calculations, gamma I is roughly 2, although this has very large variations depending on the regime. So we've seen factors of 10 in some cases different from this. So it can be larger or can be smaller depending on the regime. Okay, so then if you go back to the picture I had at the beginning of the wall and the sheath. So we have the wall here. We have the ions coming in. We have a sheath entrance here. This is the sheath entrance. We have an electric field which is pointing towards the wall. At the sheath entrance we have the ion, so ion power is basically 2 times ET times the particle flux. So here we're going to assume just that T is just the electron and ion temperatures, so for now we'll just assume that they're equal. So we have the 2E times T times gamma in the ions, and then we have an electron heat flux as well, which is roughly 5.5 ET times gamma. Inside the sheath, which remember is a very narrow layer, just a few pi lengths wide, there's a very large electric field, and this of course slows down the electrons and speeds up the ions. And so in this region we transfer energy. So we have an energy transfer from the ions to electrons, which is roughly the voltage. So I'll put this as like VF times E gives the joules, how many joules transferred, times the flux. And so this is the energy transfer from electrons to ions. And so the electrons which actually hit the wall, we've lost 3 of this, so this is just this 2.5 ET times gamma is the electron heat flux that hits the wall, and then the ion has picked up this energy, so the ions now have 2 plus this 3, so they roughly have about 5 ET times gamma. So depending on which one, whether you're interested in the plasma, so here you have the plasma is over here. So if you're modelling the plasma, then these are the heat fluxes that you need, because you care about how much heat is lost by each of the species. If you're modelling the wall, then these are the heat fluxes that you need, because when you actually get to the wall, the ions have a higher energy than the electrons, and it's this bombardment that can lead to damage to the wall, for example. Whereas if you're in the plasma, it's the electrons which are losing more of the energy.